you mean by chemical reactor in any chemical process industries? Chemical reactor basically is the heart of any chemical processing plant. Without chemical reactor we don't develop any chemical reactions. Okay, in chemical reactor we need to develop different desired products in a specific rate by reacting with an unknown reactant mixture. Basically it is a column, vessels, or any chemical. Basically it is a type of column, vessels, or tower in which different reactants are react together in a specific rate kinetics to give the desired products in a specific rate. How to proceed, it all depends upon the chemical reaction design engineers, the type of reactor, and its method of operations. Without if we don't know what type of product will need to produce, then we don't identify the type of reactor and the method of operations. For this purpose we use a specific type of reactor and its method of operation in any chemical process industries. What is desired reactor size? Reactor size is basically most important parameter in the designing of chemical reactor. It's in the form of volume, in the form of diameter, in the form of column. It's all are important dimensions to design the chemical reactor, because it's all depends upon the quantity or the bulk of chemicals to react together in a desired specific rate to produce the products. Compositions and physical conditions of product in the desired chemical products. What is its compositions in the form of liquid, in the form of gas, or in the form of solid, bulk, or crystals and amorphous solids? And what is this physical conditions and which specific temperature it gives out product? And what do you mean by explosive combustion products? And these all depends upon these factors. Temperature inside the reactor, most important factor for endothermic, exothermic reaction. For heat removal or heat addition during the reaction in heat transfer methodology, that is the temperature difference, heat exchange between the molecules of the unknown reactants during the reactions. Operating pressures is the on which pressure chemical reactor will operate to give the desired chemical products at a specific rate. And during that reaction, what pressure drop occur at the entering, at the input stage, and at the exit stage of the reactions mixture. And what factors that affects on chemical reactor design informations? First we talk about factors that affect on chemical reactor design information. The type of reactor and method of operation are good job to design the chemical reactor, as well as its position and time. If we talk about chemical reactor designing, then the reaction kinetics is most important factor for operating any physical conditions or operating parameters in the chemical reactor design information. It's all depends upon the various factors, just like endothermic or exothermic characters of the reactions. Endothermic, during that chemical reactions, heat must be absorbed in the chemical reactants during the reaction. Or exothermic means heat must be evolved or released from the products after the chemical reactions in the chemical reactor. The rate of heat addition or removal from the system and the flow pattern of fluid throughout the vessel, these are all major or important factors that affect on the chemical reactor design informations. Flow pattern, it identifies that the what is the flow pattern throughout the vessel. It depends upon the reaction kinetics as well as the its rate. Means flow pattern, laminar, turbulent, transition. It may be of any type of fluid performance of chemical reactor. It all depends upon chemical reactor efficiency. If we fail to consider these any factors in the chemical reactor design, then the overall performance of chemical reactor will economically disaster and economically drastically failed, and its performance will be decreased. Okay, now next we move on the another slide, that we talk about the symbol and relationship between the concentration of component A and the mole fraction of component A. In this slide we talk about chemical reaction kinetics between the different chemical reaction relationships. In this slide we take a special case of batch and flow system. Means batch means batch wise reactants are introduced into the reactor, and batch wise products will be produced in the flow system of gases, at which the density will continuously changing. Density continuously changing means here number of moles are not constant. If we focus on this chemical reaction, that is A plus B produce the product R. In this overall, if we focus on the overall chemical reactions, in here overall number of moles of component A, number of moles of component B, and number of moles of component R are not remain constant. Continuously it changes. That's why density will directly related to number of moles. That's why we said that the density will remain vary during this case, and temperature and pi value will remain constant. Okay, first during this derivations, here we talk about the relationship between the concentration of component A and the mole fraction. We both these equation separately derive these two equations. First we talk about the volume of fluid element that will be linearly changes with concentration. That here V equals to V naught 1 plus epsilon A x a, epsilon A. Here epsilon is the fractional change in volume in the reaction, before the reaction and after the reaction, where conversion is included or conversion is excluded. So here we take this important formula, that is V, which is the volume of fluid at time t, and V naught is the volume of fluid at time 0, and here mole fraction of the component A during that particular reactions. Okay, next we move on the concentration component of A chemical formula, which may be equals to number of moles of component A divided by volume of fluid of this element. Okay, next we take an example just like same as V equals to V naught 1 plus epsilon A x a, same as it is. Na can be replaced by this term Na naught 1 minus x a. Okay, next we know that this term will be equals to Ca. So we put so we replace Na naught upon V naught by this factor. Okay, but remaining factors will remain same in this step, and in the third step this value will divided by another side. So these two values are multiplied to each other, then we get equation number 1 in the terms of concentration of component A and concentration of component A at time 0. In the next step we differentiate the equation number 1 in terms of Ca and Ca naught and Xa, and in this equation first before differentiation we multiply and dividing by the with the denominator factors, so we get this particular equations in terms of concentration of component A and concentration of component A at time t and 0. Next we move on the mole fraction of component A. In this portion we talk about the concentration mole fraction of component A. So we have to first we have to cross multiply multiplication apply in equation number 1, so we will yield this equation, and next we move on elimination method apply on this step, then we get mole fraction of component A in this form. Xa component will remain shift in another side, remaining factor will shift on another side, that will be right hand side, and in the next step mole fraction of component A will be eliminated from this step, and we get the equation of mole fraction of component A in terms of concentration of component A and the fractional change in volume epsilon A at time t and 0. Now in the next step we follow the same step as the above equations. Here we differentiate the mole fraction of component A in terms of dCA. Before differentiation we follow the same rule as multiply and dividing the denominating factors, and we get this above solution. And if we assume that epsilon A is not equal to 0, the following changes in components will occur. We have to separate between the any chemical reactants. Next we move on another slide. We take in another short problem of Levin's pair octave 4.3 exercise, in which he has given some chemical reactions and some informations that helpful for solve the remaining factors. That will be Ca naught equals to 200. This shows that the concentration of component A at time 0 before the reaction, and before the reaction concentration of component B is equal to 100, and after the chemical reaction the remaining factor of concentration of component A will be 50. Now we have to find a mole fraction of component A, mole fraction of component B, and concentration of component B. Now we in this figure we first assume the remaining figure. In this we introduce different feeds, that is the CA0 and CB0, and in the desired product CR that will be equal to 50. Firstly we assume that the total number of moles of feed gas in the introduction point, that may be 200 and 100. If we combine these two values we get the answer of 300 number of moles of feed gas for component A. Then we first assume that for component A, so we have to find at xa equals to 0 volumes, and at xa equals to 1 we have to find volume of fluid. At xa equal to 0, when no chemical reactions will proceed and no desired products will produce, so that's why we assume that the stoichiometric concentration of component R will remain 0, so we get the answer is 300. Now when the chemical reaction will proceed and products R will be produced, when 200 when 200 moles of component A will consume to produce R. That's why we here take the concentration of component A is 0 and concentration of component B is in minus sign, because it is an disappearance of because it shows the disappearance with respect to R. So we get the we get the value of volume of fluid that may be equals to 100, and after that we will have to find more fractional change in volume for component A by using this formula. And if we substitute these all values in this equation, we have to get epsilon A that may be equals to minus 2 by 3. In the next step we have to find for component B remain as same. For when no chemical reaction will proceed, means xb equals to 0, the volume of fluid will remain as same as for component A mixture. And for when the chemical reaction will proceed, that may be xb equals to 1, here will be remain same, but only changes in component B, because in this equation we have to talk about only with respect to B. So here overall number of moles of component B or overall concentration of component B is consumed to produce the product R. So here the stoichiometric or concentration of component B it remain 0, and we get the volume of fluid element after the reaction is 200. Now we have to find epsilon B, as we will find out the fractional change in volume for component A as above. So here we have to so here we get the solution of epsilon B minus 1 upon 3, and by using these all above values we will have to find in the desired required solution xa, that is the mole fraction of component A. So we have to use this formula in terms of concentration of component A at time 0 and at time t before and after the reaction, and fractional change in volume for component A. Then if we substitute all the above values in this equation, so we get the mole fraction of component A which must be less than 1. If it is greater than 1, then it is impossible to calculate any desired chemical production. Next we move on mole fraction of component B. Same formula. By using all the substitutes for component B, then we get mole fraction of component B which may be equals to 1.8, which is not possible because mole fraction must always be less than 1. That's why we can't find the value of CB, because for finding out the value of CB we have to find the value of XB, because here value of XB is not possible to find out, because here mole fraction is greater than 1. That's why we can't find the value of CB. So my required description has been completed here and my presentation has been completed. Thank you.